Hello guys, welcome to Tichita differential equations. In the last session we saw how we can solve ordinary differential equations with separable functions, and today we're going to review a couple more examples and hopefully jump into linear differential equations of first order. So the first example that I want to review is in the form of x dy over dx plus y squared equal to 4. So if you can remember, we wanted to make it p dy plus q dx equal to 0, correct? So now I'm going to simply multiply by dx and we're going to get x dy plus y squared dx equal to 4 dx. Is that correct? So let's just rearrange this. X dy plus y squared minus 4 dx equal to 0. Now we can simply divide by, or furthermore rearrange this by dividing by x and y squared minus 4. So we're gonna end up at y squared minus 4 plus dx over x equal to 0. So this is easily solvable, right? We're gonna integrate and we're gonna end up at ln absolute y squared y minus 2 over y plus 2 plus ln x. Oh, sorry guys, I forgot we have 1/4 ln x equal to, now here I can write down c as our constant, but because on the other side of the equation I have ln, I'm going to change this to ln c, okay? Because ln c is also a constant that would make it easier for me to get to the final equation. So what I'm going to do now, multiply everything by 4 to get to ln y minus 2 over y plus 2 plus 4 ln x equal to 4 ln c. Again, I can rewrite this as ln c1. So we're getting to now, if you can remember from our first lecture, I can bring that 4 as a power for x and then write it this way, which basically now I can say and again, if you can remember, this can be rewritten as this form. So eventually I'm gonna have is that correct? So that's our final answer. Alright, let's move on to next example. So number 2, y prime is equal to 2x cosine squared y, and now we have a condition y of 0 is equal to pi over 4. And the question is, I'm not gonna write it down. Limit of y x goes to infinity. What is this? Okay, we need to find the equation of y. So simply, instead of y prime, I'm gonna write down dy over dx equal to 2x cosine squared y. Correct? And then I'm gonna rearrange, so I have x on one side and y dy on the other side. You can see how easily by bringing this over here and this here, I'm gonna rearrange to p dy q dx. Correct? So now simply integrate. The answer of that integration is gonna be tangent y equal to x squared plus c. Here, using boundary condition, right, to find c. So I know that tangent of 0, I know y of 0 is equal to pi over 4, meaning 0 and pi over 4 is gonna be on this function, x being 0, y over 4 being y. So therefore, I'm gonna have tangent of pi over 4 is equal to 0 squared plus c. Correct? So therefore, c is 1. Simple. So now, plugging c back in there, I'm gonna have tangent of y is equal to x squared plus 1. Therefore, simply y is gonna be tan inverse of x squared plus 1. So now, limit of tan inverse of x squared plus 1. So why you are doing this? That's the question, right? Remember, x to infinity is basically is equal to limit of tan inverse of x squared, x to infinity, which is tan inverse of positive infinity. So what would be the limit? It's pi over 2, because we know tangent of pi over 2 is equal to positive infinity, right? This is our final answer. Perfect. Now that we went through these examples with you, we're going to start with actually we have time for one more example, so let's review this one. So there is another function that I want to solve. So x y minus 1 dy over dx is equal to y. So again, what I'm gonna do, I'm gonna multiply by dx, right? and then divide by y, and at the same time I'm gonna divide by x. After rearranging, I'm gonna get y minus 1 over y dy is equal to dx over x. So again, this is simply integrable. And therefore y is going to be ln xy plus c. I think that's about it for today. In the next session we can start at the first order linear differential equations. Have a good day and see you guys next time.